Last episode, you learned the linear algebra running inside every layer. Tensors, shapes, matrix multiplication. That tells you what a network computes. It says nothing about how the network learns to compute the right thing.
Here's the real question. A network makes a wrong prediction. Millions of weights exist inside it. Which direction does each one need to move, and by how much, to make that prediction less wrong?
The answer is calculus, specifically one idea. The chain rule, applied automatically, layer by layer, backward through the network. That's literally what backpropagation is.
I'm Mahaz. Let's build that intuition from one simple picture.
Today, the derivative as a slope, partial derivatives, the chain rule, the computational graph, watching gradients flow backward, and PyTorch Autograd doing all of it automatically in code.
Everything in this episode builds on one picture. The derivative is just the slope of a curve at a single point.
Take any curve, say y equals x squared. At any point on that curve, you can draw a straight line that just touches it, the tangent line. The steepness of that tangent line is the derivative. Steep tangent line, pointing up, large positive derivative. The function is increasing fast. Flat tangent line, derivative near zero. You're near a minimum or maximum.
This is exactly what gradient descent uses. The derivative of the loss function tells you which direction is downhill, and every weight update takes a small step in that downhill direction.
In PyTorch, you never compute this derivative by hand. Autograd, automatic differentiation, computes exact derivatives for you, for functions with millions of operations chained together.
Real neural networks don't have one input, they have thousands. So we need partial derivatives.
A partial derivative asks, if I nudge just one input, holding every other input fixed, how much does the output change? You compute one partial derivative per input, treating all the others as constants. Notation, instead of a straight d, we write a curly partial symbol, partial y over partial x1, partial y over partial x2, and so on, one for every input variable. Stack every partial derivative into a single vector, and you get the gradient, written as a nablus symbol, grad of y. The gradient points in the direction of steepest increase of the function. Gradient descent does the opposite. It steps in the negative gradient direction, steepest decrease, because we want to minimize the loss, not maximize it.
Now the single most important rule in this entire episode, the chain rule.
A neural network is a composition of functions, layer after layer after layer, each one feeding into the next. If y equals f of g of x, the chain rule tells you how to differentiate that whole composition. The rule, the derivative of y with respect to x equals the derivative of f with respect to g, multiplied by the derivative of g with respect to x. You multiply the local derivatives along the chain. This is exactly why it's called backpropagation. You compute each small local derivative at each layer, then multiply them together going backward, layer by layer, to get the derivative all the way back to the very first weight. A 10-layer network is a 10-function composition. The chain rule is the only reason it's even possible to compute how the first layer's weights affect the final loss.
PyTorch doesn't apply the chain rule by magic. It builds an actual graph of every operation as your code runs. This is the computational graph.
Every operation, every add, every multiply, every matrix multiplication becomes a node in the graph. The arrows show data flowing forward from your inputs through every operation to the final loss value. Take a tiny example, y equals x times 2 plus 3. That's two nodes, a multiply node, then an add node, chained together, ending in y. PyTorch builds this graph automatically the moment you set requires underscore grad equals true on a tensor and start doing operations on it. Every single operation gets silently recorded. This recorded graph is exactly what makes the backward pass possible. PyTorch already knows every function it needs to differentiate, and in what order.
Now watch the same graph run in reverse. This is the backward pass, the moment a gradient actually flows.
Backpropagation starts at the loss, with a gradient of exactly 1, and walks backward through the graph. At every node, it multiplies the incoming gradient by that node's local derivative, the chain rule, applied one operation at a time. By the time the gradient reaches the very first weight,
It has been multiplied through every single operation between that weight and the loss. That final number is exactly how much the loss changes per tiny nudge to that weight. In PyTorch, this entire backward walk is one line, loss.backward. Every gradient for every parameter in the whole network gets computed in that single call.
This is why depth used to be dangerous. Multiplying many small numbers together during this backward walk can make gradients vanish, or multiplying large numbers can make them explode. We'll fix both later in the series.
Let's see Autograd for real in actual PyTorch code.
Step 1. Create a tensor with requires_grad equals true. This tells PyTorch, track every operation on this tensor. I will need its gradient later.
Step 2. Do your normal computation, y equals x squared plus 3 times x, or anything more complex. PyTorch silently builds the computational graph behind the scenes as this runs. Step 3. Call y.backward. This triggers the entire backward walk we just described, computing every gradient in the graph.
Step 4. Read x.grad, the computed derivative, sitting right there as a regular tensor. No manual calculus, no symbolic math library. Just exact numerical gradients, automatically.
Let's prove it actually works. Hand calculation against Autograd, side by side.
Function, y equals x squared plus 3 times x. By the power rule, the derivative dy dx equals 2x plus 3. At x equals 4, that's 2 times 4 plus 3, which is 11. Now in PyTorch, x equals torch.tensor of 4.0, with requires_grad true. Y equals x squared plus 3 times x. Call y.backward. Print x.grad. The output is exactly 11.0, precisely matching the hand calculation, computed automatically, with zero manual differentiation. This is the proof that Autograd isn't approximating anything. It's computing exact symbolic derivatives, just executed numerically, for functions far too complex to differentiate by hand.
Autograd is powerful, but it has sharp edges. Here are the bugs you will hit, and how to instantly recognize them.
Bug 1. Forgetting optimizer.0_grad. PyTorch accumulates gradients by default. Call backward twice without resetting, and your gradients silently add together, corrupting training.
Bug 2. Calling .backward inside a block wrapped in torch.no_grad. That context disables gradient tracking entirely. You'll get a runtime error saying the tensor has no grad_fn. Bug 3. Modifying a tensor that requires grad using an in-place operation like x plus equals 1. This can break the graph and throw an in-place operation error during backward.
The fix for all three. Check requires_grad and grad_fn before calling backward. Always zero your gradients each training step and avoid in-place ops on tensors that need gradients.
Before episode 6, run through this checklist. Every item protects you from a confusing training bug later.
Check 1. You can explain the derivative as the slope of a tangent line. Check 2. You know what a partial derivative and the gradient vector actually represent. Check 3. You can state the chain rule and explain why it's the mechanism behind backpropagation. Check 4. You understand what a computational graph is and how PyTorch builds it automatically.
Check 5. You can describe what happens during loss.backward, gradient flowing backward, multiplied node by node. Check 6. You know the top 3 Autograd bugs and how to spot each one.
6 checks. If all 6 pass, you're ready for probability and loss functions in episode 6. The math behind why cross-entropy is the right choice for classification.
Recap. What you now have before episode 6.
The derivative is a slope. The gradient is a vector of partial derivatives, one per input, pointing towards steepest increase. The chain rule multiplies local derivatives along a chain of functions, and a neural network is a chain of functions. The computational graph records every operation forward. The backward pass walks that same graph in reverse, applying the chain rule automatically at every single node. Your challenge: pick a simple function, compute its derivative by hand, then verify it with PyTorch Autograd. Post both results in the comments. Backpropagation looked like magic at the start of this episode. It's really one rule, applied automatically, over and over, through a graph PyTorch built for you.
You'll see loss.backward hundreds of times in this series from here on. Now you actually know what happens the instant you call it.
Next episode, probability and loss functions, entropy, cross-entropy, and exactly why that specific loss function is the right one for classification, not just the default everyone copies.
Subscribe. Post your gradient check. See you in episode 6.